Everyone had a good one, I think. Your homework. How every classes going? Picking up after the semester, I remember when there was like a holiday, like a Friday off, and the professors always just gave my work to make up for the day, and it wasn't really like a holiday. I don't know if that's still you're also frustrated on, but hopefully it wasn't that way in class. It's going to let down not having a classes. Sure. That's probably fucking up and there's people that are you know, I think you have that, so this is probably different. So, you know, fine, yeah. That's that. That's right. Yeah, so I was like at a professional reducing homework assignments or something over a week that has a holiday. Like what it should be. All right, well, welcome back to topic 8 now. It's our 9 of the semester here. It's like 2/3 of the way done. We're going to talk about inserting data into the database. That's our goal for this last task of the course, is how to get the data inserted into the database efficiently so that once it's in there, then Postgres can do whatever magic it's going to do and make things go fast for us. And so 2 announcements here. So quick on Wednesday, I decided we're not going to do that entire notes packets all in one Wednesday. So we're going to go up to section 9 here, which is everything that we have covered so far. Mostly. So things that we covered so far. So things that we need to know about, again, the isolation levels, about repeatable committed, uncommitted in Postgres, the repeatable read from a different one here. And when you have repeatable read, it's the sort of like snapshot of the database. As soon as you do a select from the database, so because over here I got this select that happens before the commits over here. And because so on problem 6 right there, I have this select right here that happens before all of this stuff happens over here. My snapshot of the database will be at time 4. If I didn't have these 2 select statements right here, and I only had this select statement down here at the end, then even though I did a repeatable read, this one down here in line 11 would still see the stuff that happened before it. It's just after we first access the database to read something about it, we need a consistent state. And so repeatable, all those selects were giving us zeros, whereas in any of the other isolation levels, they were changing based on the status of the other transactions. And so there's a handful of stuff about the transactions there, and the locks. We can try to, or that you understand whether the locks conflict with each other or don't conflict with each other. And depending on the types of locks that are required, you could run into the deadlock situation where you have 2 different sessions that are waiting on the other session and neither one can make forward progress. And then you have to be able to understand like implicitly what's being created. So like on a command like this, being able to look up to see there's no lock table in some particular mode. We have to figure out what mode Postgres is locking for us implicitly to know if it was going to block or not block. And then there were low levels. We talk about some different debug techniques to figure out what those are actually currently locked or not locked. And so as we're working through studying preparing for the quiz, those are good tools to make sure we understand the what's going on in the database. And again, what those tools look like is in the topic 7 transactions. In the middle of the notes, there's a bunch of these links to the references over here. These two are ones that you'll have to be able to reference for the quiz itself. These two down here are useful for actually like debugging, working through the problems in Run, because they allow you to run these or explain what these commands are doing to help you figure out the internal state of Postgres. Now on the quiz, you'll have access to a computer to look stuff up, but you're not allowed to run Postgres environments. And then we talked about section, the unique constraints. Without unique constraints, we needed 2 tables to cause a deadlock, 2 separate locking systems on 2 different tables. But with unique constraints, we can get a deadlock on just a single table. So the quiz, be very careful about unique constraints. The example quiz that I passed out, there was a problem here with unique constraints that is sort of hidden. But it's this second problem right here. This table T, A into primary key. And so I'm not saying unique constraint anywhere, but you have to remember that what a primary key is it's just a column that has a unique constraint and is not known. So this has a unique constraint, so we have to think about all the weird things about unique constraints on a problem like this. And then so more of these row level locks. And I think this is the section that we ended up on last time. And I was trying to remember if we fully got through this or not last time. And I think we might have only gotten partway through. So, but either way, I think it would be good for us to do a little bit of a refresher on here. And so let's take a look at problem 51. We're going to do problem 51 here. I don't think we did that one explicitly. To remind yourself what's going on with this row level constraints. This again, section 9 here is the last section we're going to be responsible for the quiz on Wednesday. And we're a little bit more material in the packet here, but save that for after Wednesday. And so as we're getting set up, we're going to do problem 51 here. We'll spend, I don't know, it'll take 10 or 15 minutes or so. And that'll be all the stuff that we're going to talk about for the quiz on Wednesday. After we finish this, we will talk about your homework assignment for this week. So if you have questions about what we're talking about here, how to work through these problems, how to get a picture of why do we care, anything at all, make sure you get those asked while we're talking about this problem, because we're going to do a transition after this problem to something else. Okay, and let's see, hang on. Let's go super close. Let's go. And then over here, so we'll make sure that the scroll is running, the code is down. I'm going to break it down first, so we're going to fresh state. I don't remember where we were with the problem on the other one. So I'll just bring it all the way down and then up -3, send it to the background. And then on the right hand side over here, let's start up simple inside the PG database. So this section on both of them, I need to put inside of simple. So it's do it like that. So then a nice debugging command that I think I mentioned last time is \bang. Lets you run shell commands inside of psql. And so I could, if I wanted to do something like \bang ls, if I wanted to know what the files are in my current folder, but I don't care about that. I just wanted to hang my scroll up here and the reset command. Okay, we're on problem 51 over here. So create table 2 is problem sorts the same way as a lot of them, and then inserts into table values 9. We're going to change that 9 to 10, and then we are beginning in a committed isolation level on the left-hand side. So begin, it's the same as begin isolation level committed, which in Postgres also happens to be the same as uncommitted, but in particular is different than repeatable. So I would just do again, because that's what the problem says, but it would be the same if I had done either of those two other options. And so that is the transaction on the left-hand side. And again, what we have to do on this quiz is figure out how these two transactions that are happening simultaneously interact with each other. The right-hand side, we're now going to enter the repeatable isolate level. Isolation level, repeatable, semicolon. And then that was timestamps 5 and 6, timestamp 7, update 2, set A equals 1. Update 2, set A equals 1. And notice there's no where clause at the end of this update command. And so it's code we have an update or delete command without a where clause. And what it's done is it has applied the table level lock, the very unrestricted table level lock. We need the row share update table level lock, I believe, if I remember correctly. But it has required a row level lock, which is restricted on all of the rows in the table. And we know it's applied to all of the rows in the table because it applies to every row where this command applies, and that is row in the table. Because there is no where clause. And now line 8, to delete from T where 8 equals 10. On the right hand side here, delete from T where 8 equals 10. And this is command blocks. We're observing the blocking behavior right now. And so then under the quiz, you're not allowed to just run this and observe what happens. You have to predict if it isn't going to block by looking up the row level blocks of the delete command over here on the right hand side. With the update command on the left hand side. But on the quiz, I'm going to annotate this with a circle. Notation for just some and we'll take that with a circle along that. And then let's have a table here with happening on both lines simultaneously. We'll never have something where two lines happen simultaneously. Maybe it will happen on the left hand side. Or on line 9 over here. And commit that, semicolon, hit enter, and what we're going to observe on the right hand side is this could not serialize access due to current update on the right hand side. And so this command here not only blocked, but also errored. And so not only we have to circle, but we have to exit out. And so the question that you might be asking yourself is why exactly did it error? And so we have to remind ourselves, what does this delete command, how do these row level blocks work? How do the row level blocks work? And it's always in two stages. First stage here, so there's a where clause. We find all the rows that match that particular where clause at the sort of beginning of time before the changes on the left-hand side fully take effect. And so everything I'm talking about right now, talking about what's happening on timestamp 8 over here. Find all rows that match where back. So it's at the beginning of time course, like the beginning of this particular time, beginning of one of these. And beginning of line. And so at the beginning of line 8 right here, this transaction has not committed. And so where 8 was 10, this particular row right here, the line 3 row is what matches. Line 3 row is what matches at timestamp 8. Line 3 row is what matches. And then in the second stage, what we do. So we're walking after this point, we found all those rows, we required our lock for the delete row. And this, so we tried to acquire the lock, that lock is waiting on the update command on line 7 over here. And so we can't actually acquire that lock until it commits. After we're able to finally acquire that lock, after acquiring, so after Acquiring. We recheck this for the weird part about the low level lots. We recheck the condition. We will check the condition, and we only apply the command to the row that apply that we check the condition. Right. That is fine. We check condition. And so this was, so the week from 2 equals 10. After giving the update t set equals 1, this 10 value is no longer equal to 10, it's equal to 11. And so we're not going to delete that row from the 1. And so this delete command actually would be nothing. The reason it's going to is because of this repeatable read isolation level, and it read that same row twice and got 2 different results. So the first time it read it, it just before timestamp 8, it got the value of 10. And then after it read it, after timestamp 8, after the left hand side's been committed, we got the value of 11 because the update command over succeeded. And so that gave me an error due to the repeatable read isolation level. If the repeatable read isolation level had not been there, then we would not get an error, but it would not do anything because where was row 10 that had previously been matched, no longer satisfied that condition, and so it would not actually work. A lot of things there, a lot of confusion. Maybe we jump too fast into the stuff that we were talking about last time. Getting our brain to change to run, but does that make sense? Do people have questions about that? Yeah. Yeah, so the question is here that I had the typo making 2 lines happen, 2 commands happen at the same time. This is a typo, and it should be that this command happens on line 9. That's the 49 value. And yeah, sorry, but also to write that out. That's the change that it was supposed to be. So yeah, the commit here, the left hand side committed before the right hand side was what was supposed to have happened. Should actually change the behavior of this problem either way, but it was really the same result here. With the repeatable read here, the delete throws an error. Again, it throws an error because it's a rare condition was checked twice. It's checked once at the beginning of the line before acquiring the lock, and it's checked once after the line after acquiring the lock. And because the value of that row changed, things are not allowed to change on the repeatable read, we're getting an error message. If there had not been a repeatable read, then we would not get an error message, but we would not actually delete anything from the table. I think we talked about this last time. It's weird that we don't delete anything from the table because this is what the problem 50 appears. It's weird that we don't delete anything from the table because after we run this line right here, after we run line 6, it's I'm pulling 9. After we run line 6 right here, we update 9. 9 goes to 10. This makes 9 go to 10, and 10 go to 11. So there is something that matches this delete clause. There is something that matches this delete clause after we do the final commitment, and that first row which would match the delete clause. But because the check here happens in 2 stages, one before the lock and one after the lock. Before the lock, it only acquires the lock, tries to acquire the lock on the second row down here, and then it only does the operation on the those that it had acquired a lock on. It didn't acquire a lock on this first one, so even though that first one got updated to a 10, it won't get deleted, and nothing will get deleted on this problem. The difference again between problem 49 and 51 is that in 49, in the new middle isolation level right here on line 5. And so it's okay that we'll get two different read values in my delete command, one before and one after. Okay, there's no error from that. But on line problem 51, we do get an error message because of the repeatable read isolation level, because when I read before and after the delete command, I can check this where clause twice. It's there's two different values, and that's not allowable in the repeatable read, so we get an error message. That's so hilarious. I jumped into this problem too fast today. I totally lost everybody. Again, there's an example quiz. So we can see sort of what to expect as core problems on it. Problems just follow one of the sections in that notes packet, and again, going up to section 9 was what they're responsible for. And tricky thing to be aware of, remember primary key implies a unique constraint. So if you see primary key, then we should be thinking about the unique constraint problems. I'm going to send you that one, please. What's it going? The whole purpose of this quizzing is to prepare us for the homeworks. Easy quiz will be the homework. Fortunately, this next homework is not going to be able to have really any of this isolation level stuff, and you have more practice with the quizzes in your lab this Friday, getting more experience with this before your next homework assignment, which is going to really need this information. We'll switch gears now. We're going to talk about our next homework assignments and supplies. So if you go to the topic 8 SQL and Python folder, there is this homework Postgres folder inside of it. And that is your next homework assignment for this week. We're going to spend the rest of today talking about this homework and what you have to do to complete it. So this homework begins with 32 points instead of 16 points. And notice that there's two sets of test cases over here now. There's going to be two databases that we're working with. And so we'll have to get both of these test cases to pass to get full credit. Each one's worth 16 points by itself. So you can correct. Each one's worth 16 points. It'll turn out that this denormalized line is super easy to do. It's just a one line in your code, which I will show you here in a minute how to do it. And this normalized one's going to take the most effort. And again, our goal here, we're repeating the Twitter Mavericks assignment, but this time using Postgres. And again, because there's sort of a lot of things going on here, it's going to be broken up into a number of parts. And so in this first part, we're just going to be figuring out how to use Postgres from within Python. Focusing on inserting data into the database and understanding JSON or denormalized versus normalized schemas. And Postgres. I'm going to switch over now to the terminal and walk through what the structure of this project is, because it's a little bit different than what we've seen before. So I'm coming over here, and we'll just get one wide terminal this time. Let's repeatedly. Let's go to the project slash Postgres folder. Here is where my stuff is. If we build components, we'll have these files as well. I was this morning just taking some notes here on these files. So you'll see that I have some modifications. But a nice Git command that I use fairly often was git clean-fd. What this does is it deletes all of the modifications that I have made to any one of my files and resets them back to what they are in the Git repository. Another command I can use for that is git checkout. Normally, you probably use git checkout for switching branches, but if you have a file name after git checkout instead of a branch name, it will take that file back to the previous location it was in the index or in the repository, in the history. And so git checkout dots is the same thing as git clean-fd. Git checkout dots taking it back to the whatever the counts for us. So now I can get status and we're back wherever you want. We open up the Docker Compose files. Anytime I see the projects with the Docker Compose file, it's one of the first things that I do is take a look inside it. There. And so there's two services that you'll notice inside of this Docker Compose file, two database services, a PG normalized and a PG normalized. We're inserting data into two different databases and seeing how it works within those two databases. You notice there's a bunch of environment variables set right here. We'll make those in a second. You'll have to pay attention to those. And the reports are also going to be adjusted. So let's see. I'm just going to do the normalized one for now, and I will adjust this report to 2.4. That sounds good to me. Just maybe that number, I don't think anybody else is using. So together, it's going to goes up -3, and I'm going to bring up the normalized one right now, since that's the only one that I made the edit still important. They will have to eventually make edits to the reports and bring it to and the PS which things loaded up, but here is my PG normalized database right here. LS, LS-R. The next thing that I do, I'm looking at a new project that was a Docker-based project, so Docker Compose, take a look at that. We look at the services next, because that's where I expect to see the information about my two different databases. Again, ls-r, a nice command to be able to look inside multiple folders at once to be able to compare and contrast them. And so here I'm comparing my denormalized to my normalized databases. And see that they have the same sort of structure inside of them, but they might have different Docker files with different schemas. So let's do a vim command to take a look at those Docker files and compare them. And so what I will do is vim services /star/Docker like this *space-p. For blogs again, we'll expand to be match this Docker file and this Docker file. This inner blog right here matches the folder name, the service name, and then this one out here matches the Docker file. And then -p allows me to open multiple files at once inside of them, and I can go back and forth between the G2 commands. And I noticed that they are basically the same, so that simplifies things for me. But I also noticed that line 1 up here is different, so the base image again that we're going to use services from. And that scares me a little bit. This one looks nice to me. Past me was nice to you all and decided to specify a version number here. But the past me was evil to you all and decided not to specify a version number here. And so I remember all the struggling that there was on the version numbers of some of our first Docker assignments. You anticipate having to deal with that a little bit on this one as well. This one, so we'll figure out which of these two Docker files I'm looking at. You take .eo with you, it's the file name, so it's the normalized database. While you're working with that, you might encounter some version issues. And in fact, I believe we will. We'll just have a sort of do a full one to expect from it in a little bit. So the Docker files, now the schema files, like this, comparing the two of them. So this is the denormalized database that I'm looking at. I can tell because down here in the top bottom of the corner, it shows me the denormalized file name over here. And here there's only a single table in the denormalized database, which contains the JSON V table inside of it. And at least in the sort of modern real world engineering practical database world, this is what people mean by denormalized. Denormalized. It's basically synonymous this way these days with JSON. In Postgres, there are two JSON types, JSON and JSON-B. JSON, there's JSON-B. JSON was added, it was the first JSON type added to Postgres, and it's kept around for historical reasons, but it's a plain text type, it's really slow, and so nobody uses it these days. Immediately in JSON over here stands for binary, and this is what everybody uses these days. The interface between the two is 100%. It's just JSON-B, there's a lot more data efficient and a lot faster, so everybody uses JSON-B. So there's one table here again, data JSON-B. And the contents of this table, what it's going to do is it's going to be recruits that are loaded in from our data sets. I'm going to load them for a second here, and press Control Z, set it to the background, take ls. So there's this test data.zip file. There's going to be the data set that we're working with for this particular assignment. And let's just see how big this data set is. I use my familiar unzip-c command here, which will unzip this file and send it to the console, the super console. We'll click that to wc-l to see that there are 10,001 lines in this file. So it's not a super large data set. The reason why we are using this small data set at first is because it's something that, like, all the data can fit inside of this Git repository. You all can get your data loading commands working well on this small amount of data. We can upload it to GitHub Actions and have continuous integration that runs and verifies that everything works correctly. And then after we get everything working correctly on this small data set, then we can transition over to using the actual real large data set with gigabytes of files. Yeah, let's do one. Let's do away fag for the actual one here. No, two. There we go. There's an actual. So those are the JSON intros that will be on your current mapping assignment. Probably works sort of from there, big giant blob, a bunch of stuff. All this gets sort of crammed into this one entry, one column inside of those rows, inside that JSON type. Okay, and then on the right hand side over here, this is the normalized database, and normalized more or less means they've broken out the tables into many different tables, all with many different columns, and they are hard coded with a bunch of types inside of all those columns, and primary keys and foreign keys, not null constraints, and so forth throughout the database. I'm going to come real quick over to our project instructions again and scroll down to this picture. There's a nice little picture here of how all the tables work together, and those may or may not help you after working. One last thing I'll say about these schema super files over here is that there are no views inside. There are a small number of views inside the all of these two views right here inside of the normalized. Inside of the denormalized file, there are many views. So both of these files are about the same size. But for these views, only denormalized file will give us sort of a consistent interface into the JSON blocks, into the JSON-B type. So here, again, on the left-hand side, I'm on the denormalized database. And I have this create view groups right here that selects a whole bunch of stuff from this data field. This data field is this data field inside of the tweets JSON-B, what the JSON actual object is. And then these areas over here are in Postgres and how we'll access information in the JSON-B type. So this syntax like this is equivalent to this syntax in Python. This syntax down here equivalent to something like over. One weird thing in Postgres here is that you'll notice sometimes there's these like single arrowheads and sometimes there's the double arrowheads. For internal weird postgraph reasons, the chaining multiple sort of subscript operators, these operators right here called subscript operators. These operators up here also called subscript operators. In postgraphs, we are chaining these subscript operators. The last one has to have a double arrowhead to get the actual string or integer type in a single arrowhead to the left of it in terms of JSON B type. So this view down here gives us a like access to the data that is consistent and exactly has the same exact form as these tables over here. So here's a users table right here has this set of keys. And on the left-hand side, I search for the users here. And so right hand side, I search for the tweets. This tweets viewer on the right hand side matches the tweets viewer on the left hand side. The tweets table on the right hand side in the normalized database matches the tweets view here on the left hand side. So once we get all the data loaded either way into the two databases, we'll have a consistent way to access it. Your last assignments, you will have the right like SQL queries inside of those SQL. There are a bunch of sort of those SQL queries that ran inside of this SQL folder, but you don't have to do anything. I've already provided the sort of solutions to these problems right here. So -p SQL/star like this opens up all of those files, and you can see that I've already provided a bunch of sort of complex-ish code for these. At the top, it says sort of like what the problem is supposed to do, and then at the bottom, it has the code that does that. And again, because of the views on the denormalized database, this same code will give you the same exact answer with the and the expected results also the same expected star. These are, if you've loaded everything incorrectly, then these are the results that you'll get for all of those queries. So you don't have to do anything with like verifying your code works. The only work that you have to do is getting the data into the database. When you get the data into the database, then we run the run tests command like normal, and it will pass all of those problems that are in the script. We'll talk about how to get the data into the database here next. Have any questions about? Take a picture of what the daily assignment, what the assignment's doing. Okay. So there's the two test cases. GitHub Actions. I always look at the GitHub Actions like directly to see what's going on inside of you. And I continue to after moving the basic setup stuff, it first runs this load.sh and then runs the run tests.sh. The denormalized test up here runs it on the denormalized database. The only difference between the test case for normalized and denormalized is that the normalized test case runs it on the normalized database. They're both on the same load tweets code. The first thing that we'll have to do is load tweets code. Getting this shell script to actually load the tweets in. The denormalized one down here is the easiest, so we'll start with that. We'll go back over to the notes for this week in the topic 8 folder. And scroll down. So at the top here is just some notes about the JSON type. I mentioned this already, JSON B is what everybody uses these days. So some things that I didn't mention, so JSON supported the killer feature, was a killer feature of MongoDB, we needed a NoSQL system. For this reason, NoSQL became super popular around like 2010 to 2014 timeframe. 2014 is when Postgres actually added SQL support or added JSON to SQL. And so these days, sort of standard recommendation is do everything in Postgres because it can do everything that these NoSQL databases like MongoDB can do. And here's the invitation we'll talk about as well. Here, the 4.5 though is how to actually load the data into those denormalized database. And we're going to use the copy command. Copy is a super fast command. And there's this big long incantation down here that you just can copy and paste into the load .sh file. We can modify the stuff in infographics right here to be appropriate for your our setup. Homework problem, the implementation that will load all the data. And so just get those correctly, get all those little brackets correct, stick it right here, and you'll have 16 points on the problem right away. Yeah, if you're interested in what's actually going on behind all of this stuff down here, that link right here explains the filtering and why this is the right way to load things into a JSON project. You also use date worth throwing links. Any questions about how the flow of links will things come from? Other parts is going to be the normalized release, so that's what we're going to spend the rest of the time doing. Connecting with those videos from Python. Well, then there's some startup code here for doing this. It's this load step for Python. And takes a little bit of care to get this Python file correctly connected to the database. And so .sh file, they're going to have call the Python file right here. And if we're going to say Python Joe load tools.py like this, we're going to get an error message about this --BE argument and --inputs are going to be required. The inputs is easy. This is just to name the file that you're working. Just go ahead and set it here. The --DB is a little bit harder, and it's something we haven't had to deal with because we want to have one database. Python scripts or whatever we've been doing have been working inside of the database. In this case, our load tools.py is running outside of the database and not inside of the database. I'm going to open up the GitHub action again. And we'll notice that so like the run test that is running inside of the database, inside of the Docker controllers like this. But the load tools.sh is not running inside of the Docker container. It's running directly in the Lambda server. And so with Python code, it's going to be running directly on the Lambda server, not inside the Docker container. And we're going to that's -d command is how you're going to connect your Python code here with Python code to the database container. Go ahead and open it up. DB arguments. So this is the command right here that actually does the connecting to the database to the args.db that we're passing to this. We use a create engine function inside of Sigma Alchemy. We use a special sort of URL format that looks like this. It is a PostgreSQL scheme. This thing to the left of the slash is called the scheme or schema. The URL, the PostgreSQL, and then the username, password, host, port, and database. And all of this information right here, all that information is inside of the Docker Compose file. So user, password, all that. So inside here, the port number that works, and so load trains.sh. Right here, we're something like code, load trains.py, --inputs equals $sign file. I'm not putting the test data.zip here and doing the $sign file because eventually your next assignment is going to be replacing this files variable with a list of like the real zip files in the data set. And so even though there's only one of them, and I hard code it, I'm going to use this file variable from the program so it's ready to go to this group over a whole bunch of stuff. And then the --dv will be the post. Let's go and // and then all the stuff, the information from the so the Postgres user will be Postgres. Postgres. The username, colon, password. Postgres, colon, password is just a pass over here. Pass. The host is going to move the whichever one leads to the databases that you're connecting to. So in this case, it'll be EG normalized down here for the normalized, the Python as well as the into the normalized. Copy and SH stuff is going to be normalized, so PP normalized, very good. Whenever we specify the first ones, the one on the left-hand side, it's the port that's being exposed to the Lambda server, so the 23344. Once you get all of that correct connection there on configuration, about hit over, then your load tweets that the WAV file should actually run. The Python file itself, though, you have to make some changes to the Python file. So, chat those tweets that line like this. We're going to walk through the Python file next to see like what is occurring and what sort of changes they're going to have to move to. Yeah, so files divided into subparts, a bunch of helper functions up here. You're not going to have to touch the helper functions. They're well commented, so if you're interested in what they're doing, you're welcome to take a look at them, but you don't need to modify them at all. The parts that we have to modify are this insert tweet function right here, where there's this fix me annotation about what you have to do. I'll just do a quick search for insert tweet so that you can observe that down here in this function down here, that's the if name of this name. So if we're running this Python program as a script, which and create a database. So we talked about that. Now, so this args.db will connect to something outside of the container. And then this moving through the input file, all of this like giant set of for loops from what vaguely familiar from the MapReduce stuff, but they're looping over all the contents of the zip file, looping over everything in the zip file, printing out the current timestamp so I can monitor what's going on with that data insertion. And then loop over every line in the file. You're extracting the tweet from that JSON context. And then instead of in the MapReduce, you're doing, I don't know, counting up how many times different words are being used. You're calling the insert tweet function on your tweet JSON type. Insert tweet hints for tweets and the connection to the database. So there's a connection to the database as well. There's a few SQL sessions. And so I have right now in this first homework, we're only doing one insertion at a time. It's only one session going on. So there's no realness about the locking and blocking and deadlocking and all of that. Eventually, coming back up here to the insert tool, we have to do for this. I have a bunch of commands for you that you'll have to fill out. Adding the secret code into the Python. This first one up here is already filled out for me. So this first one is selecting the ID tweets for a tweet where ID tweets is whatever the tweet is. And we're just checking to see if it's already inserted and we'll see it. So this is required because there's a unique tweet constraint on the data table. And so if we were to insert the same tweet twice, then our program would crash. So this prevents our program from crashing if the same tweet goes in twice on the same. And we're starting a transaction right here. Line 106 starts the transaction. But this is the part that is looking for certain versions of SQL where the versions weren't good. For certain versions of SQL Alchemy, this will work as written. For other versions of Alchemy, what's going to happen is that for Polygon, and say like P-Super would have a select domain that happens outside of transactions, but this one up here is not inside of a transaction. The select domain that is not inside of a transaction. And so this is inside of an implicit transaction. Select above inside an implicit transaction. So it's like automatically adding the program and commands around just this select field. But for the newer versions of I'll say first the older versions. Older original version of SQL Alchemy does what it did for my code when I was originally writing this. It's automatically ends the transaction after this select field. Automatically ends the transaction. She ends for transaction. But for newer versions, the transaction not ended automatically. And for this, we'll create an error when you try to use this connection doc again, creating a new explicit transaction inside of one of the implicit transactions. This causes an error. When it creates a new transaction inside the implicit transaction. So the construct in Python connection dot begin. It's going to automatically create the begin, call the begin command for us in P-Simple. When we enter this block, and automatically call the commit for us when we exit this block. This code that you're likely to encounter will assign is just figuring out the right error messages related to that. And then everything else here is pretty straightforward, but I've already given you a pretty good template on all the locations where you make to write a SQL command. So anytime there's one of these sort of big comments like this, there's a simple variable that here we'll have to create what the SQL command will look like. Where always with insert command, insert into, we have to figure out, okay, we're inserting into the users table right here. So insert into users, and then I'll load up inside of them over here my schema for the users table, which is at services/gg normalize/schema, edits, search for users down here. And then here are all of the fields that I'm going to have to add to the users table. My users created at, updated at, and so forth. And so insert into users, the list of the columns, ID, users, created at this, and then values, whatever those actual values are going to be. So as a temporary example. This text type is a special wrapper around strings inside of the SQL Alchemy library, and so you can't just directly pass strings to the onto the database. You have to pull into this text type first. For all of these, insert string command, but then you just like a spot to put this text, giving you this function called to text. After making that function call, you're going to have to actually connect to the database with this connection.execute like this. So we'll scroll up to the example where it's already done the select statements that we're copying as results right here. Copy that right here. And it's connection.execute SQL. It's something like this. That's what we'll have to do. One of the common mistakes that students are beginning with programmers make, really Python programmers with the people on it. With this is we use our Python knowledge of string like editing to create a SQL command for us. So common mistake, first I'm going to first write something right now that is bad, and then I will fix it. So the common mistake is, for example, there are the F string type in Python, which would allow us to say, create this string variable for us at the Python level, user ID Rogos, something like this. ID user, so this is like a tweet variable, something like who's user that's the kind of the user. We should do something like this to get the ID of the user and pass it over to those files. And this will work like 99% of the time. Similarly over here, for the creating that, we could do something like tools creating. And this will work 99% of the time. Until you have an evil user who is trying to break your system. And you can expect that I'm a little person trying to break your code. So this will not work for you all for this segment. Instead, what we have to do, I'll put in a little bit why what the bad thing is that will happen to this. But the correct thing to do is instead of doing this, don't do this, which means don't insert data at the Python level, don't insert data at the Python string level. Instead, what you should do is what this text to type does, what it's function right here, is allows you to create what are called query parameters. It's traditional to make the names of your query parameters match the names of the columns that we're inserting, but it doesn't have to match. You can do whatever you want. Where it adds this. And then down here in the execute command, we can provide a dictionary which fills in the values for us, and it'll be the Postgres that's filling in the values for us instead of Python. So syntactically, that looks like down here we have ID users, the ID users right here. This matches this ID users. This is the text function up here identifies this as a query parameter because it starts with a colon, and so it's something that it will substitute in for us automatically from this dictionary down here. You have the Postgres level, and so I pull this as my ID users. So I put that right here, and that's what will get substituted. And then similarly for creator at the tweets created out. Thanks. Now it's time to add. So 15 columns that we have to add in here to all of those. And this is always the correct way to do this. Again, I'll flip it out. It was never correct to construct a simple program that inside Python. What is how I have to do it. There's this, is the basic outline of this command right here. Every one of the tables that has data inside of the database has information that has one of these sort of formats for to insert. And so right here, there's another simple command to insert, and you'll have to add the appropriate text inside here to to do that. We're going to talk about. Any questions about I still need to get that string, it does not correct either way. We'll go without the F string, a little bit nicer without the F string with the signals, makes it more obvious that there's no background manipulation. Question. Yeah, that's a good question. So the question is, so we have those users to insert a bunch of columns into it. And so for the column list over here, that's going to match this column list over here. Just I don't know with the first two of these, but then we add all the other columns down here. And so that's where columns comes from. But then the actual question is like the values. How do I know what goes into the values? And for the most part, it should be fairly obvious. Like there's just a little cool that field inside of the truth. Every one of these fields matches something that's inside of the truth. We're in a time where it's not like a literal character for character match of what's inside the truth. If it's an ID into another key. So in the raw JSON, if there's a URL in the raw JSON, it'll have an actual URL and not an ID URL. In order to get the ID of the URL, we have to call a function, which is get ID URL function, which I've already written for you, and it gives us user ID URLs right here. And so down here, when we get to the ID URLs part, that will just be ID URLs or user ID. If there is something special like this that's going to insert into the table, something special where there has to be some sort of pre-computing that happened inside Python, then I've done all that pre-computing for you. So, for example, in the truths table, the next thing to insert there is the truths table right here. There is this like geometry here. There's not an actual geometry field inside of the JSON, but there's a geometry variable that I constructed up here. Yeah, this geostring is a variable that goes into that geometry. Similarly, there's a that's the only just to think about yeah, so all of these other ones are just more or less straight out of the just not such a very straightforward. When we get onto the truths table down here, though, you'll notice that there's an ID users. ID users, what we're going to stick into the ID users column, where the user ID we will also add up here as well. So I have to occasionally reuse some values from the previous table and subsequent table. There's a lot of little edits like this that have been made, but in the past students have found that like once it's not until done the first one, that all the other ones go pretty quick. And I think that's everything about the assignment with your this first to talk about. Okay, all of those changes and then push it together, we should pass to read and and go print it. And then all the hard part here is just getting the stuff into the database, and the queries about what's in the database are already answered for you. And everything. This is up here. I did not put code and put IDRL. This is that's that ID URLs like this. If I have a hole inside of it in front of it, that means that it's this query parameter, something that will be handled at the SQL level by Postgres, and yeah, there you won't be vulnerable to something called SQL query injection. Great question. Any other questions? One last final note then for us for today. Back to the notes that we are scrolling down. There's notes about properly escaping your inputs. So there's this woman, Rachel True is her real name, and she was using Apple products. And Apple could not handle her name at all because they had an error in how they were handling their Postgres system. Somebody at Apple, instead of using this query substitution, used the Python was manually constructing these queries, and so her name True was being inserted as a Boolean True instead of as the text like string True. And so she was locked in with her Apple accounts for 6 months. There's this famous XQCD comment about little body tables. So if, for example, in one of the tweets, and there is a tweet that is like this, there is like the text of a tweet, so something like say a tweet text was equal to some malformed SQL query. Closing whatever the semicolon is, semicolon here, and then now a drop table using semicolon. And this over here will match with the substituting the symbols of close and end with a previous SQL command. Then this would start a new SQL command that would actually like modify and delete things from my table. And it's very, very hard to manually write SQL code inside of Python that's not vulnerable to a malicious attack like this, where somebody has handcrafted something designed to break your system. But this code that was very well tested. It doesn't have any of those security vulnerabilities inside of it. Here's the SQL injections. Not super common on one super common like when I was growing up in the early 2000s. Basically, every web page had SQL injection on it. LLMs these days, for whatever reason, very often want to construct SQL code by hand. So they're using clock pillars. They will maybe 10% of the time construct SQL queries by hand instead of using the proper query parameters like this. And so a lot of codex generated web apps these days are vulnerable to SQL injection. Any more questions about this one? Besides, let's Portal 4 working example for us real quick because there's a lot of moving to this. I would say inside this created app, the created app was closing this quotation mark right here, closing things. Whatever the quotation mark is previously open, sending point and command, and then now I can type in whatever command I want. I've done passwords to be wherever I want the passwords and passwords to be equal to, or so So it's just by modifying one of those values to something that's like partial correct SQL. We'll make it SQL injection. Probably not connecting enough dots before we have to answer the question. How can I make more dots than that on them? That's fine, I think. That's for today. Sorry, I'm just talking, rambling away today. Maybe there's some questions about the time or anything else. We'll stay right with those answered. Otherwise, we're sure you're prepared for your quiz on Wednesday. Just working with those problems, make sure you understand how those problems look like. Yeah.